What's up, everyone? Let's talk about fine-tuning language models with just the forward passes. So there's a couple of important aspects in this paper. Just forward passes means there's no backward pass bottlenecks while fine-tuning, and it's crucial. Like, they only do this for fine-tuning because obviously when there's no back propagation, these techniques that we'll discuss in this video, they usually work for cases where we have a good initial point, like a good pre-trained model, and then you're basically trying to fine-tune on top of it. Let's jump right into it. Going over the abstract, back propagation requires prohibitively large amount of memory, and then these guys discuss zeroth order optimization, where the principle is basically to estimate gradients. I think this is the key. So they're talking about estimating the gradients without doing back propagation. And if you remember, like, basically back propagation with the chain rule while training a neural network is basically we have a loss function, then you calculate the derivative of this loss function with some weight. And this basically is what needs to be calculated when we are doing back propagation, because with stochastic gradient descent, SGT, the update rule is like some learning rate, and this is how the weights are updated when training. And the key idea of this paper is we use zeroth order optimization to get rid of this step. And how we get rid of this step is by estimating this gradient with just forward passes. We'll get to this, how this all works. And it's memory efficient because now you don't have to store the gradients and you only need to do forward passes. So there's no gradient storage, there's no activation storage, and it's similar to doing inference. Let's say we have a pre-trained model and then we're just doing inference, and then we only need to do forward passes. So inference usually takes less memory than training a network. That's what they say here. They have the same memory footprint as the inference. And so memory efficient zeroth order, MeZO, achieves comparable performance to fine-tuning with back propagation across multiple tasks and up to 12 times memory reduction. And MeZO can effectively optimize non-differentiable objectives, so maximizing accuracy or F1. Now, generally, with training neural networks, we focus on having a differentiable loss function. That's why we do squared error loss, or any loss like cross entropy. All these losses are differentiable, and because we need to calculate this value while training. And the idea is, because we're not doing this back propagation, we're not calculating the exact derivatives. We only are doing forward passes, so we can estimate any objective function. We can estimate accuracy or F1 score. So this L loss function can be any objective that we're looking for. So this is an added benefit that we get with zeroth order optimization. We'll discuss how this thing actually works. Let's get to the introduction. Parameter efficient fine-tuning. Just a fraction of the network parameters, but still need to catch many activations throughout the model. They do better than parameter efficient fine-tuning because there's no backward pass. Classical zeroth order optimization. Zeroth order stochastic gradient descent uses only differences of loss values to estimate the gradients, which just forward passes through implementation. Still doubles the memory overhead. Now, what does that mean? Let's discuss this for a second. So if I'm doing zeroth order stochastic gradient descent, then we need to do 2 forward passes to estimate the gradient. And how does that work? So let's say I have a loss function, L, and so the first forward pass will be, let's discuss how we estimate gradients. So we have this function, and if I want to estimate gradient at this point, x, and we're talking about f of x, then if I want to estimate the gradient at this point, then I'll do x plus epsilon So you basically move up a little bit, calculate the value of the function at this point. You do x minus epsilon, which is a small deviation towards the left of it. Calculate the value of the function at x plus epsilon and f of x minus epsilon. And then my gradient estimate will be this line. Basically, this is the estimate of the gradient at f of x. So like you can imagine, so my gradient estimate, which let me call delta f of x by x at x, will be f of x plus epsilon minus f of x minus epsilon divided by, you basically calculate the mean deviation by going forward and backward and divide by twice epsilon. Now, here's the key. Because this is the estimate of the derivative, and I said we need 2 forward passes, this is how it's calculated. So this is my first forward pass, and this value is my second forward pass. Is that clear? Let's wait here for a second and see how this thing is functioning. So how do you calculate f of x plus epsilon? And remember, we're talking about parameters of the model because this is what we're trying to estimate, right? The gradient of loss with respect to, let's say I have parameters in the model. It's a neural network, W1, W2, let's say 2 parameters. So I'm trying to estimate the loss with respect to the parameters. So my x in this case will be, I'll be varying my parameters in this case. So when I say I have to calculate x plus epsilon, I'm saying for each parameter in the model will be deviating on one side, and that'll be my first part of deviation. So I'll be basically calculating f of all the w's. Let's call this set my theta, which is the parameters. So I'll be saying theta plus epsilon, and then this is my first forward pass. So you basically calculate the loss value by passing theta plus epsilon, and then you calculate the loss value by changing the parameters on the other side, so theta minus epsilon. And then once you have these 2 values, you can estimate the gradient by del theta would be, let's say del theta I would be f of theta I plus epsilon minus f of theta I minus epsilon divided by twice of epsilon. Now we'll modify this a little bit because there's some drawbacks to this method when we only change gradients based on a single value epsilon. We're basically limiting the gradient estimates that we're calculating. So the trick that they use in this paper while estimating the gradients is, instead of using a single epsilon for changing the parameters, and they basically add some variation to it. And you can understand this. Let me show you an example that if we have, let's say, theta 1, theta 2, theta 3, and these are my parameters in the model, and I'm trying to estimate the gradient, and the goal is to understand how the loss changes when these parameters are perturbed. So basically the gradient of the loss function at a particular value of these parameters. Now if I'm only changing these by a constant value, theta 1 plus epsilon, theta 2 plus epsilon, theta 3 plus epsilon, there's some bias that I'm introducing to this process. And that's because, let's say this is my function. If I'm only changing each parameter by a fixed value, let's say we have 2 parameters, y and x, and I'm trying to perturb both these parameters in certain direction. And at this point, if I perturb x, there's a big change that'll happen as compared to y. Or let me pick a different example. So let's say this is my function, and I'm looking at 2 parameters, x and y. Let me remove this. And at a certain point, if I'm changing epsilon and this is minus epsilon. I'm changing x by epsilon, and then I'm also changing y plus epsilon, and then I'm doing y minus epsilon. Changing x basically brings a bigger change to my function as opposed to changing y. And this basically means different parameters have different gradients, like different impact on the loss. And I want to understand this process by changing these parameters differently. If I change the same amount of gradient in each direction of my parameters, the impact, like I'm not adding randomness, so I won't be able to tell which, like how big is the gradient change with respect to each of these parameters, and that's what we are trying to understand. So the point is, instead of changing the gradients equally across all the parameters, and also while calculating the derivative, we basically divide by this value that we change. So if we change all these parameters by the same epsilon, then like you can understand this, the denominator will be same for all the parameters. So it's not that consistent, and we need to add more variation to this process. And studies have shown that if you do this variation of gradient estimation, then it converges faster because there's more randomness to the process and actually is closer to simulating the actual gradient descent. Okay, so now coming back to how can you modify these epsilon variations, like add some randomness to this process. So what we do is we sample a z vector from a standard normal distribution. So this is the mean, this is the variance, and this is the standard normal graph, and it'll basically, let's say this is 1, this is -1, -2, 2. So the z vector is basically sampled from this distribution. And what I mean by this is it'll be a value that acts as my, like, adds randomness to this perturbation. So epsilon, I pick, let's say, a very small epsilon. Epsilon, let's say 10 to the power -3. This is my epsilon that I need to vary. And then now I have to change this value. So I basically multiply this epsilon. Let's say I have 4 parameters, theta 1, theta 2, theta 3, theta 4. I'll basically have 4 epsilon values that I want to pick for each of these parameters, and then I'll multiply each of these by this sample vector z. So z will basically be of dimension equal to the number of parameters in my model, and it'll be sampled from standard normal. And then I'll multiply this epsilon by the z. So there'll be z1, z2, z3, z4, and that adds randomness to my process. So there'll be an epsilon, and then some of this will be epsilon times z, which might be on the positive side of things in my distribution. Some of them will be epsilon z minus, like towards the negative side of things. So I'm changing my epsilon value by multiplying it with a factor of z. And instead of using a single constant epsilon, now each of my parameters are basically perturbed by this value. So there's z vector corresponding to the value corresponding to that parameter, and then you multiply that by epsilon. And then this is how it's calculated. So you have, let's go here. So first forward pass, I'm trying to estimate the positive side of things. So I'm trying to go towards the positive side of the perturbation. So I'll basically do loss of, let's say, my parameter theta plus epsilon z vector. So for all the parameters, so theta I, zi, so this is my L plus. Similarly, for L minus, this is my first forward pass. Now for second forward pass, I'll calculate the negative side of things. So we moved up, and then now we have to go down. So L minus will be theta minus, now epsilon z can be, because z is obtained from a standard normal, so it can be positive or negative. So to make sure that this L minus is always towards the left of my vector, I basically change this epsilon to -2 epsilon times z. So you multiply it by a factor of 2. So it's always on the left of this estimation, and then this is my L minus. And then now I have two forward passes. I have the perturbed parameters for each of this epsilon z value, and then I can basically calculate now L plus minus L minus, and then twice of epsilon. That's my gradient estimation that I can estimate for each of the parameters. Remember, this is for parameters. Each of the parameters by just using two forward passes. I don't need any backpropagation. This is the gist. Okay, so let's get back to the paper. Classical zeroth order stochastic gradient reduces memory consumption to same as inference. Okay, let's come to this algorithm 1, memory efficient zeroth order optimization. This is what I explained in a little bit. So L plus, which is the positive side of gradient estimation, you basically perturb the parameters by epsilon, and then I'll get to this part S, and this is the important part. Perturb parameters. You basically generate a z vector from standard normal and change the parameter based on a small epsilon value, and then multiply that with the corresponding z value in the vector. So for L plus, you use epsilon, the value epsilon. For L minus, we use minus 2 epsilon. So our negative estimate is always towards the left of the positive value in the function. And so this value will become theta I minus 2 epsilon z. That's how L minus is calculated. Now let's talk about this seed function that they really care about in this paper. And the seed function is basically a random number generator. Let's say I'm generating random value z from standard normal. Now if I set the seed to 1, 2, 3, 4, then my random number generator will basically generate the same set of seeds. So let's say z1 is 0.1, z2 is 0.01, z3 is 1.2. So if I use the seed 1, 2, 3, 4, this will always be my sequence. It'll follow the same sequence of generation for these z vectors. And that's what they mean when they set the seed, is basically if I'm starting from a single seed, then my sequence of z vectors will always be same. And we need this because when we're doing estimate of gradients, we need to generate the same set of z vectors. Otherwise, if we generate different z's every time, then the estimates won't be correct. You need to use the same z vector to estimate the gradients. And the key here is it's called memory efficient because you have the seed. I think that's the key contribution in this paper. Because you're using a single seed, you can generate the z vector, same z vector every time. So you don't have to store this in memory. We don't need to store all these values for all the parameters. Now let's say I have 1 billion parameters in my model. The cardinality of z vector will be 1 billion because it's generated for each of the parameters. And imagine storing the z vector in the memory. It'll basically be 32-bit floating point times 1 billion. So this will be the amount of memory required to store these bits. Instead, if you use the seed, you can always generate the sequence. And so when you're multiplying these values with the epsilon, you don't have to store 1 billion parameters, 1 million z values. You can keep generating and then keep multiplying with the z values to calculate these gradient estimates. So this is the key key contribution in this paper that they talk about. This is the gradient estimation plus epsilon z minus epsilon z divided by twice of the perturbation value. Z belongs to the dimension of the parameters, and then it's sampled from standard normal. This technique is called SPSA. Talking about memory efficient, they mention here generator by S and resample the relevant entry of Z. So once you have a single seed value, you can always resample the generated Z every time in the process. We reconstruct the MeZO trajectory using a single seed value instead of storing all the parameters. So that's why it's memory efficient. Now they talk about different extensions of how you can estimate the gradients when you have to use some history for, let's say, um, momentum, and if you're using some other technique as opposed to stochastic gradient descent. But yeah, and basically the gist is you use a single seed and you can estimate these gradients using two forward passes without storing all the values in the z vector. And then they've discussed several variants on how you can use the same technique for different types of optimizations. But yeah, this is the main idea. And the results are actually pretty impressive. If we look at the results, MeZO and MeZO low rank adaptation, it's actually pretty close to the more advanced methods requiring much more memory as compared to MeZO. And then it's beating, in this case, we report zero shot linear probing and MeZO fine tuning with full parameters. MeZO outperforms zero shot and linear probing approaches with much less memory. So all in all, I feel like it's a very good approach to fine tuning in a memory efficient way. And then we have seen papers. This technique has been used in federated learning quite a bit because it's a very memory efficient process, and then federated learning requires you to transfer parameters of the model across the network from clients to the server. And this technique, because they're using a seed, and you can always recreate the z vector using a single seed value, so you don't really have to communicate with the parameters across the network channel. So it's just pretty efficient. And I see this technique being used a lot for fine tuning, at least in federated learning setups. Also, it's memory efficient, and inference is always less resource intensive. So all in all, very handy technique. And yeah, feel free to try it out.